Okay, let's look at this problem that you voted off the island. This car speeds up from rest, and we're told that after 5 seconds it has an omega final of 30 radians per second. Now this is a rotational kinematics problem. You solve it in the same way you would solve a linear kinematics problem. You make your list of the 5 variables. But remember, these are analogous to the linear variables. Delta x is the same as delta theta, and linear acceleration correlates with the angular acceleration, linear velocity, angular velocity, and time is time. Now in this problem, it starts from rest, so the wheels aren't turning, and after 5 seconds, we have a final omega of 30 radians per second. And the first thing we're looking for is this angular acceleration, and that makes the delta theta the who cares. Now, if we don't know delta theta, we don't want to know delta theta, we should use the equation that doesn't have delta theta in it. And that's just this one here. Omega final is equal to omega initial plus alpha delta t. This is going to be 30. This is 0. I'm looking for alpha. And what I get is alpha is equal to 6 radians per second every second. And I go up here and I put that in. Now, the second part of this problem, I think, is what got it voted off the island. And that's what we covered right at the end of class on Wednesday. You remember we jacked up my car, we got the wheels spinning, and we wanted to know how fast the car would have to be moving down the road in order for the wheels spinning to not screech. We called that the rolling without spinning condition, actually just the rolling condition. And what it was is that the velocity of the car is equal to the angular velocity of the wheel times the radius of the wheel. So in this case, after the 5 seconds have elapsed, the radius of the wheel is half a meter. My omega is 30 radians per second, and that gives me 15 meter radians per second. And that doesn't sound right. You want your speed in meters per second, so we just drop the radians. Since a radian is equal to a meter divided by a meter, this is the arc length over the radial distance. It has no units. I can drop it whenever I want to, whenever it's inconvenient to have it there. And so the answer to part B is 15 meters per second. Part C asks us to find the delta theta. That now is elevated from who cares to worth $87,000. And so we have 4 pieces of information. There are 3 different equations which will give us the right answer. I'm going to choose the second kinematic equation. That's going to be 1/2 times 0 plus 30 times 5. And 0 plus 30 is 30. Half of that is 15. 15 times 5 is 75 radians. Okay? Now, I want to point out that because of the operational definition of velocity and acceleration and position, I not only have this equation relating the linear motion of the car with the angular motion of the wheel, but I can also say that the distance down the road, how far you get down the road, is equal to how much degrees, or radians rather, your wheel goes through, multiplied by the radius of the wheel. I can also say that the linear acceleration of the car down the road is going to equal the angular acceleration of the wheel times, again, the radius of the wheel. So all of these linear variables are related to the angular variables through the radius of the wheel. Okay? Check that your neighbor's on the bus, please. Okay, we're required by the university to evaluate every class every semester, and so I'm going to ask you to fill out these forms. Now that you've told me what you think of me, let me take a moment and tell you what I think of you. I'm currently serving on a search committee where we're trying to hire a new faculty member. And we've been doing a lot of Skype interviews with people around the country who have applied for the job. At the beginning of that Skype interview, I have insisted to be the first one to talk. And in every case, I give them what I honestly believe is the good news. And that is that the students at MSU are the best students in the world. They're hardworking, they're honest, they're intelligent, and it's just a blessing to have a job where you can work with people like that. And I don't blame you for that. That's not your fault. It's your parents that did a good job. I blame them. So thank you for making my job the best job in the world. I plan to be buried in my backyard. I'm never leaving those. We're going to talk about stability, and to do that we need to take a field trip. We need to go to a nice field of snow, and if we hike through that snow, we'll find a pond of ice, and it happens to be frictionless ice. Who would have guessed? We put a standard meter stick down on that ice, and if I push on that meter stick with a 50 Newton force to the right and a 50 Newton force to the left, I taught you that when you add up forces, that gives you net force of 0. 50 to the right and 50 to the left add up to 0. And by Newton's second law, as I taught you, that stick has 0 acceleration. However, if I apply that 50 newtons to the right there, and that 50 newtons to the left there, I still taught you that that adds up to 0. 50 to the right plus 50 to the left. And I taught you that if the net force is 0, by Newton's second law, the acceleration of the stick had to be 0. And yet, in your heart of hearts, you know that that's not so. You know that what's going to happen is that thing is going to rotate. And what that means, my friends, is that I lied to you. I lied. Okay? However, there is a point on this stick that doesn't accelerate. Which is it? At the center. Sure enough. And so my lie was a tiny one. There is a point that obeys Newton's second law. We call that point the center of mass. Now, up until now, we've dealt with small things that we haven't worried about their rotation, or we've thrown them in such a way that they didn't rotate. And in those cases, we could ignore the truth. Okay? And when we drew our free body diagrams, no matter how complicated the object, we drew it as a dot. And that dot represented the center of mass of the object. And we didn't care where the forces were applied on the object. We just cared, are they to the left, are they to the right? That's what mattered. Well, now, if we deal with rotation, the truth is a little bit different than what I taught you. I taught you F net equals ma, but in truth, it's just the acceleration of the center of mass that is given by Newton's second law. Now I can illustrate this with a little demo. I'm going to need a catcher. Would you catch for me? What's your name? Colin. If you'd get down over there, I'm going to toss this to you. What I've got here is a system of 2 tennis balls, and in between, all the way on the other side, in the middle, I have an orange ping pong ball. Not ping pong. Yeah, it's a ping pong ball. Now, the whole thing as a whole makes a complicated motion. Send it on back, Colin. And that's just messy. However, if you can get yourself to focus only on the ping pong ball, only see the ping pong ball, ignore everything else but the ping pong ball, you're getting sleepy. Okay? If you can only see that ping pong ball, you will see that it follows a nice smooth parabolic path given by Newton's second law. Now, if, on the other hand, I move the ping pong ball away from the center of mass, now when you watch the ping pong ball, it has a very complicated motion. Sorry about that, Colin. Send it on back. Okay, now, don't go anywhere. I've got another system. In this system, and in the previous section we broke the ping pong ball. I'll pay for that. Clearly, the center of mass is not in the center of this system. We've got a heavy softball here and a light tennis ball. And so if you watch that orange ping pong ball, it does not follow a smooth path. It has a complicated path. Send it on back, please. Now, we've rigged this. We've set it up so that the center of mass is right there next to the softball. And so now, if you watch the ping pong ball, it should follow that nice, smooth, parabolic path. Oh, and over his head. That's how we broke the ping pong ball. My bad. Perfect. Let's thank Colin, folks. So, no matter how complicated the motion, there's a point called the center of mass. We can't see it, but it follows this nice, smooth path. That happens to be my son Christian. He's a dentist, and in 3 weeks he graduates as an orthodontist. I'm going out to his graduation. And here he's doing a little flip, and my son-in-law caught it on camera. And I submitted this picture to my publisher. I have a textbook, and I wanted to put that on the cover of the 7th edition. My publisher called me up and said, hey, really? I mean, that's a really funny-looking kid. And I said, yeah, but he's my funny-looking kid. And the guy says, yeah, but he's still funny-looking. And so they ended up putting a picture that was similar in many ways, but with a very handsome, athletic guy that was not funny-looking. And he's a nice kid. He's a nice kid. Now, to find the center of mass, it's just like finding the average of your grades, your grade point average. Now, I hacked into the Canadian higher ed system, and I found the transcript for my friend Jeff Adams, and you can see that he's really good at physics, not so good at other things. But he's got an A, he's got some C's, and so I would estimate that he's got a GPA of, what do you think, B? Yeah, that's not the way we do it. What we got to do is we have to recognize that physics is more important than calculus. You knew that in your heart, right? I mean, it's 4 credits and calculus is only 3 credits. So what we have to do is we have to take each grade and we have to weight it by how many credits that grade represents. And if we do that, then Jeff Adams' grade point average is a 42, which seems high, but it's Canadian, right? It's inflated. No, we've got to divide by the weighting factors, the credits. And if we do that, we find that his GPA is a 2.5. Now, in truth, Jeff Adams just always got A's in everything. He's one of the most brilliant people I know. But I know someone who hasn't, and that's me. I got accepted to MIT because I had really, really good grades. I was the big fish in a small pond at my university. There weren't very many physics majors. And I got to MIT and I found that every nation in the world sends their geekiest students to MIT. I mean, it was the center of geekdom. And I found that I was behind. I did not measure up to these geeks. Now, in your graduate courses, everyone pretty much gets an A or a B. You know, the top half of the class gets an A, the bottom half gets a B. And that first semester, I got straight Bs. I was the dumb kid in the class. And my dad called up. He was so excited that I had gone to MIT. He was so proud. He goes, "Greg, how did it go?" "I got a 4.0. "That's wonderful, that's wonderful. I knew you could do it, I knew you could." I forgot to tell my father that MIT is on a 5-point scale. Yeah, I feel bad, but that's the way it was. So the second semester, I got things figured out. I got caught up, and I started doing well. And I got straight A's the second semester. My dad called up, "How did you do?" He said, "Straight A's." "Same as last time." Silence. He still doesn't know. He thinks I got A's all the way through MIT. It didn't happen. Now, in a system, if we want to talk about the center of mass, it's usually pretty straightforward. If I have something like a beam that's made out of uniform density wood, then the center of mass is going to be, well, in the center. And if I want to quantify that, I set up a coordinate system called 0, the left end. And in that case, my center of mass would be located at 2 meters in that coordinate system. Now, if I added something, that's going to move the center of mass. Your gut tells you it's going to move to the right. But how far? Well, we need to do a weighted average. We take the center of mass of the beam, which is right at 2 meters, and we weight that by how important it is to the system. It represents 50 kilograms. We then add to that the center of mass of the box, and we have to weight that by how important it is to the system. It's 25 kilograms. And then we divide by the weighting factors, the kilograms, and what we get is the new center of mass would be at 2.33. Now, for a more complicated system that had more than 2 objects, we would just extend that formula, just adding up all of the center of masses times their masses, and then divide by the weighting factors. Now, there's another concept called center of gravity. And in most applications here on Earth, we use center of mass and center of gravity as synonyms. They mean the same thing to people. But technically, they're different. The location of the center of gravity is defined a little bit differently. I take the center of the first object, and instead of weighting it by just the mass, I weight it by its weight in newtons. That would be m1g. And then I take the second object, and I weight it by its weight, m2g. And then I take the third object, and I weight it by its weight, m3g. And then I divide by the weighting factors, m1g plus m2g plus m3g. And I know what you're thinking right now. You're thinking, hey, well, why don't you just cancel all those g's and you'll get the same definition you've got for center of mass. And that's true. If you're looking for the center of gravity here on the surface of the Earth, where all the g's are 9.8, you get the same answer. But if you have a more extreme case, let me show you. When the Earth pulls on the moon, it pulls on the center of gravity. That's where we can consider that force to be applied. And that center of gravity is not at the center of the moon. That's because when I multiply by the g's here, in this example here, the g's aren't the same at every part of the moon. I've got a bigger g here than I have here, because the back of the moon is further away from the Earth. Now, the moon rotates about its center of mass. Okay? However, the pull by the Earth is applied, or can be thought of to be applied, at the center of gravity. Now, this has a consequence called tidal locking. You'll probably have heard that when the moon goes around the Earth every 28 days, it does so such that the man in the moon is always looking at us. So as it goes around, the man on the moon's just always facing the Earth. Kind of creepy, huh? And the way that happens is this force is applied offset from the center where it rotates. And so if you think of my head as the moon, as the moon's going around the Earth is always grabbing my jaw and pulling it towards the Earth. Okay? And that's what forces it to always be pointing the same way as it goes around. See if your neighbor understands that. And that will not be on the final exam, that piece there. Okay? That was just in case you were interested. Okay, let's talk about stability. Are we stable? No. How many of you been to the Leaning Tower of Pisa? Any of you? No. Were they letting tourists up in the tower when you went? Okay. When I went there, I was 8 years old. I was terrified of the tower. It didn't seem stable. And fortunately, my father was just way too cheap to take us kids up there. But suppose that an entrepreneur came along and said, you know, we could make more money with this thing if we just made more room for more tourists. So let's just build it up one more story. And it goes unstable. Now, if you take a standard high-rise and you build it up one story, it doesn't fall over because you're moving the center of mass up, but you're not moving it over. But with the leaning tower, when you build up one more story, you're not only pulling the center of mass up, you're pulling it to the side. And here's the key idea. As soon as the center of mass gets beyond the foundation, it goes unstable. Okay? So that's the first big key idea. Now, you've probably heard about the Suzuki Samurai. Do you remember that car from years ago? It got recalled. Do you remember why? It tipped over. You know, it'd be going around a corner and it'd just fall over. And some people didn't like that in a car. And the problem is they built it up too high. They built it up, it was very sporty, and it had a very high center of mass. And so when it was going around a bank turn, you could get that center of mass out over the wheelbase, and it'd just fall over and things. Anyway, another example is the tourist buses in London. You know, they've got the double-decker and the triple-decker buses, and they fill those up with American tourists, which are heavy. And that brings the center of mass up high. Now, to make those more stable, they actually put large plates of lead along the bottom of those buses to lower the center of mass so they are more stable. Now, here's a way to actually make money with this idea. If you go to a bar with your friends and you keep your wits about you, as it gets closer to closing time and your friends get pretty drunk, bet them any amount of money that they can't put their heels up against the wall and touch their toes, okay? And if they're drunk enough, they'll make the bet, okay? Now, as you lean forward, you move your center of mass forward. And as soon as the center of mass gets beyond the toes, you fall over. Your friend can't do it. There's no possible way. The center of mass on a human your age is about 1.5 inches behind your belly button. On a human my age, it's like 7 inches behind. But still, it's behind my belly button. And as I lean forward, that moves it out, and then I tip over. If I'm not against the wall, I can touch my toes. That's no small feat for a man my shape. Why can I do it out here? The caboose, yeah. The caboose goes back, and that keeps the center of mass above the feet. Okay. Now, you might have seen these pictures on the interweb. This is someone that went over the side in his car. They're pulling it out. But the center of mass got out beyond the... Yeah. So they brought a bigger truck. And... Yes, indeed. Unstable. Now, here's something you can do if you get engaged and you want to impress your new in-laws and they invite you to dinner. Right in the middle of the dinner, just grab your fork, grab your spoon, ram them together so they'll never be quite the same. Take the toothpick that you were picking your teeth with and use that to balance this, maybe not with that one there, balance this whole thing on the edge of a glass. Stop. And then if you really want to impress your new mother-in-law, take a match light both sides. Are they going to love you? Welcome to the family. Any questions? Yes, sir.
It's kind of hard to see that from back here.
You couldn't see that from the cheap seats back there. Okay, well, let's do it again. Green Acres is the place for me. There we go. Okay. Oh, physics is fun. That'll be our toothpick. And I borrowed these instruments from the ground crews 23 years ago. They never got them back. Okay. Now, can you see that? Now, this leads us to our second key idea of only two.
No fire?
No fire. Bring out the flamethrower. An object is stable when its center of mass is above the foundation. But that cannot be the case here. If I look at the mass, it's all down here. The foundation is right there. That's what it's balanced on. It can't possibly be, the center of mass can't possibly be above that point. So our second idea that we will understand on Monday is that if it can't be above the foundation, it will seek a point where it's directly below the support. Now that tells me that the center of mass for this system, these objects have mass that come out this way, that center of mass has to lie somewhere below that point right there, which means somewhere along this bar. Okay, and that is the second part of our concept. Now, this allows me to do this very dangerous demo. Not dangerous for me, but dangerous for my trained bear. This is Bobo. And Bobo has been practicing for a long time to get ready to do this for you. Yeah, you can do it. Come on. Okay, come back and try again. Whoa! Yeah, okay. I'm coming to get you, Bobo. Hold on, hold on. Okay. Clearly, either Bobo is very, very talented, or there's just no way for him to fall off. And I think it's the latter. You see these lead weights down here? That ensures that the center of mass is below the wheel. And indeed, symmetry suggests that it's directly below the wheel. And so that means that if Bobo tilts a little bit, that center of mass is going to seek a location, again for reasons we'll understand on Monday, directly below the support. So it'll be pulled back directly below the string. And if he tips this way, it'll seek that location directly below the string. Now, how many of you have been to the Science Museum in Seattle? Did you ride the...
Yeah.
Yes. Okay, they've got a little Schwinn bike here, and they've taken off the rubber wheels, and you can ride it around this great big ring that's way up high. And that's my lovely wife up there, and you can see how it works. Attached to the bike is this long bar, and there's a heavy, heavy weight at the bottom there. And if you lean one way, that brings the center of mass out from underneath the support, the ring. And as we just said, that center of mass is going to seek a location, for reasons we'll understand on Monday, below, and will bring you back upright. Now you can see she's not very worried about that. I, on the other hand, am terrified. This is not my first time on this ride. My first time, this is my second time, my first time was years before when it was a brand new ride. My kids were young, and we, as all geeks do, had a season pass to the Science Museum. And so we went there when this was brand new, and my kids pressured me into going up into the line and waiting and doing this. I was nervous, but I got on, and I got halfway around and freaked out. I just leaned over, and suddenly I just froze, and I couldn't move. And there was a 16-year-old guy that was running the event, and he just started talking me in like I was on the ledge of a building. You know, if you just push with your right foot, now push with your left foot. You can do it, you can do it. Come on, come on. Took him about 10, 15 minutes to get me around. People were waiting in line. I get off, I hug the guy. He tries to teach me the physics of what I was saying. I understand the physics.
I'm just scared.
Folks, have a great weekend. It looks like we've got something else going in the room right now, so let's get out of here.